In this section, we will talk about three basic principles that govern motions, known as Newton's law of motion. There are three fundamental law of motion, and these principles were first presented by Sir Isaac Newton in the 17th century, and these three laws of motion describe the fundamental principles that govern how objects move and interact with force. It is also interesting that when Sir Isaac Newton was working on this three fundamental law of motion, he also concurrently developed the calculus and law of gravitation. And one thing we can also look at is what do we call the study of motion, where we will talk about the forces causing the motion as well, and this is called dynamics. So we said that the study of motion is called kinematics, and we said we study displacement, velocity, and acceleration in kinematics, and we never talked about the force. And in dynamics, on top of what we study in kinematics, we will also study the forces causing the motion. So dynamics is basically kinematics plus forces causing the motion. Let's start with Newton's first law of motion. Newton's first law of motion is often called the law of inertia. Inertia is an object's resistance to any change in motion, and it's directly related to object's mass. The law states that every object will remain at rest or in a uniform straight line motion unless an unbalanced or an external force acts upon it. Essentially, an object will keep doing what it's doing until something pushes or pulls on it to make it stop or change its motion. And for example, we can see the animation here. If a car suddenly stops and passengers are not wearing seat belt, they will continue moving forward due to the inertia, because initially the passenger was in motion, and when the car suddenly out of nowhere stopped, the passenger uh, the mass the object or the mass of the passenger's body will try to remain in motion, and as we can see, uh, they will continue moving forward due to inertia and possibly being thrown in a projectile motion. And this is why seat belt are essentials. They provide the unbalanced or an external force that stops passenger from flying away from the car. And we need to define this as well. We define this inertia, and we define this inertia as the resistance to change in motion. Now let's talk about second law of motion. Second law of motion gives us a way to quantify how forces affect objects. This law tells us that an object's acceleration is proportional to the force applied to it and inversely proportional to its mass. So what it says, an object is the acceleration of an object is directly proportional to the magnitude of the imposed force. That means acceleration is directly proportional to the force, and this is we read this as directly proportional, meaning if the acceleration increases, force increases. If the acceleration decreases, the force also decreases. And it also says that the acceleration of an object is directly proportional to the magnitude of the imposed force and inversely proportional to the mass of the object. So acceleration is inversely proportional to the mass, meaning if the mass increases, the acceleration decreases, and if the mass decreases, the acceleration increases. The more force you apply, the greater the acceleration, but the more mass an object has, the less it will accelerate for the same amount of force. It's simply an elegant relationship, and we can sum up this relation like if we combine these two proportionality relation, we get the equation F is equals to ma, where F equals to force, m equals to mass, and a is equals to acceleration. And we can see from these two plot. In the first plot, we can see the mass is bigger, and we can see the acceleration. Since it's a vector quantity, the length of the acceleration represents the magnitude, and we can see it has a smaller acceleration and for the small mass, and for the same force and small mass, we can see the acceleration is high for a smaller object. Here we have the final equation. So I will write what these are. F equals to force, m equals to mass, a is equals to acceleration. And since we are talking about force, so first we need to define what is force. Force is a push or pull, whether the object is moving or not. The effort to push or pull is called force, and force is what causes the acceleration on an object. The relationship is direct that we can use it to define the unit of force itself. And so if we look at here, we define that force is equals to mass time acceleration, which gives us the unit of force, as kilogram meter per second square, because if we say F is equals to ma, we know m is mass, and the unit SI unit is kilogram, and a is acceleration, and the SI unit is meter per second square. And if we combine these two, 1 Newton will be kilogram meter per second square, and the dimension of the force is mass length over time square. Dimension is nothing but the physical quantities, right? So the physical quantities we use for defining force are mass, and we denote mass as capital M, length L, and time. And based on this formula we can also define what is 1 Newton, and 1 Newton is the force required to accelerate 1 kg mass by an acceleration of 1 meter per second square. So 1 Newton force is required to accelerate an object of mass 1 kilogram by 1 meter per second square. So based on this relation we can also define what is 1 Newton force. Now let's look at an example to understand what is force F equals to ma, and we talked about the force in the previous equation where previous slide where we said force equals to ma, and here F equals to not just force but net force. We generally call it a net force. And one thing to remember is any physical quantities where the relation is based on a vector quantities will ultimately result in a vector quantity, meaning force is also a vector quantity because it depends on acceleration, which is a vector quantity. If force is a vector quantity, that means it has both direction and magnitude, and we will follow the same sign convention we have been doing. We will say force going in a positive toward right is a positive, and force that's oriented toward left is a negative. And we should also know that there can be more than one forces acting at an object. For example, here if you see we have 2 Newton force going this direction, a 10 Newton force going in this direction, and the acceleration is caused by the net force between these two forces. So if we have even more forces, then the acceleration that we said is equals to ma, in the acceleration that depends on force, the force itself will be the net force, and the net force is the total effect of all the forces acting on an object. For example, if we have these two forces here, two forces in here, and if we want to calculate the net force, what we will do is we will sum up all these forces. So generally you will see, if you read a book or some other articles, generally what you will see is F net is equals to summation of all the forces. This sign is called sum, and the meaning of this is called sigma. This is a capital sigma, Greek letter sigma, right? And the meaning of this sigma is sum of all. And generally if you read the books, you will see the net force is equals to sum of all the forces. And sometimes if all the forces, when you sum all the forces and the result is 0, that means the net force can be 0 even with many forces. And when we say acceleration, we are mostly interested in, when we say force causes acceleration, we are mostly interested in external forces, uh, because as we can say, and we cannot push a car from inside, right? So we have to go outside and push the car from outside in order to move the car forward. So we are in order to cause an accelerations to an object, we are mostly interested in external force, and we are not interested in the internal force, because internal force cannot cause acceleration. And as the name suggests, external forces are forces acting from outside the object. Now let's look at this example here. So we have a force, one going in left direction, and the magnitude of the force is 2 Newton, and another force going toward right, and the magnitude is 10 Newton, and we want to calculate the net force. And as we said, the net force is the sum of all the forces, and we also said that the force going left is negative, force going right is positive. So we have uh, net force is equals to force going left, force going right, and then of force going left is minus 2 Newton, plus force going right is positive 10 Newton, and if we sum this we will get 8 Newton. And if we want to draw the resultant force, since the magnitude since the direction of this resultant force is positive, or we can say towards right, if we want to draw the force, this is what the F net force, F net would look like. Now let's look at this conceptual question. Here the first question says asks us two equal magnitude horizontal forces act on a box. Is the object accelerated horizontally? And what it's saying is we have two forces, one acting in positive direction, another acting in negative direction, and the magnitude is the same, and is asking whether the object is accelerated or not. So in order to answer the question, first we need to know the net force, right? And the net force is the sum of all the forces, and we have one negative force plus one positive force, and since the magnitude of these two forces are same and the direction is opposite, net force is 0. That means you cannot that means we do not have any acceleration on this object. Now for the same question, is it possible that the object is moving since the forces are equal in size but opposite in motion? So we said that the acceleration is dependent on the net force, right? So the acceleration depends on the net force, and this question, however, is not asking about the acceleration. It's asking us whether a box is moving. And as we said from the Newton's first law of motion, what did we say? The object will remain as it is, meaning if it's in rest, will remain in rest. If it's in motion in a straight line, it will remain in motion without any external force, right? So if the object was already moving, that means the second case where the object was in motion, now it will try to remain in motion even without any external force, right? So even though the net force is zero, and the even though the net force is zero, it is possible that the object will be moving, because initially it may already be moving, and if there's no external force, that means it will keep moving because of the first principle of motion. And now let's look at an example numerical problem. A 60 kilogram bicycle and a rider accelerates. So mass is 60 kilogram, accelerates at 0.5 meter per second square. This is a square. Acceleration is 0.5 meter per second square, and the question is asking how much extra force was applied. So what is the force applied on the object to have an acceleration of 0.5 meter per second square? So from Newton's second law, we know force equals to mass times acceleration, and the mass is given 60 kilograms and acceleration is 0.5 meter per second square, and if we multiply this is 30 kilogram meter per second square. This is called Newton, so the force is 30 Newton. So if you don't want to remember this, you can remember that the unit of force is Newton, and we generally denote Newton as the letter capital N to denote 1 Newton. So if you remember the relation between the derived unit of force, then you can easily convert it into other unit. If you have to convert it into empirical unit or other even other metric unit, for example in milli or mega Newton. And now for the second part of the questions, it's asking what is the acceleration of a 20 kilogram cart if the net force is 40 Newton. Now instead of force, we need to calculate the acceleration caused by a force of 40 Newton on an object with mass 20 kilogram. So mass is 20 kilogram, net force is 40 Newton, and we need to calculate accelerations. So from the second law of motion, we know F is equals to ma, and now we need to calculate acceleration, so we can isolate a from here, and if we isolate a will be F over m, and F is 40 Newton over 20 kilogram. And if you do not want to convert this Newton into this basic unit, then you can use your knowledge of the units and just say your acceleration is 2 meter per second square. However, if you don't remember this and you want to uh, remember the unit of acceleration, then you can go back and convert this unit. So basically this is 2 Newton per kilogram, and Newton is kilogram meter per second square, and we have all kilogram here, so kilograms cancels out, so we have 2 meter per second square. So basically we use the same relation F equals to ma to calculate both force and acceleration based on the given condition. And we also need to know about the difference between mass and weight. In day-to-day life, we simply use mass and weight interchangeably. We sometimes say, oh, my weight is this much, my mass is we generally don't say the mass is this or weight is this. Which in day-to-day life we generally use it interchangeably. However, they have a different meaning. Mass is a measure of an object's inertia, and the unit of mass is kilogram. And weight, on the other hand, is the gravitational force acting on an object. Uh, Weight is a gravitational force acting on an object, and the unit of weight is Newton. So as we said, this is a gravitational force and the unit of force is Newton, so the unit of weight is also Newton. And we should know that in a in a scenario where there's no gravity, an object will have the same mass regardless, even if there's gravity or not. However, the weight of the object will be 0 if there's no gravity, because weight is defined in terms of gravitational force. In other words, we can say an object's mass is the same everywhere in the universe, but its weight can change depending on the gravitational pull. The weight of the same object will be different if we were to take the weight on the surface of Earth or on the surface of, for example, Moon. And mathematically, the weight is given by mass times acceleration due to gravity. Here G is acceleration due to gravity, and the value of G is 10 meter per second square. And we can see an example of weight and mass. For example, 10 kilogram mass on Earth is in 10 into 10 is equals to 100 Newton weight. So if 10 kg is the mass of an object, then it will be 100 Newton in term of weight. Given the acceleration due to gravity is 10 meter per second square. Now let's see an example where we have a multiple force. We talked about the net force and we defined We also look at this relation where we said F net equals to sigma F external, and this is generally read as sum of the forces. Now let's look at here. If we want to calculate the net force, summation of all the forces, and using our sign convention, positive, negative, F net will be, we have 25 Newton positive plus 5 Newton, this is also positive, and then we have 10 Newton force in negative direction, so the total net force will be 25 plus 5 is 30 minus 10 is 20 Newton. And if we want to calculate the acceleration caused by this net force on the object, and we can see here the mass of the object is 5 kilogram, then we know F is equals to ma, and F is the net force, so this is 20 Newton is equals to mass is 5 kilograms times acceleration, and if we isolate acceleration, this will be 20 Newton over 5 kilogram, which is 4 meter per second square. Sorry, this calculation is wrong here. This will be 20 Newton. 20 Newton, 20 over 5 is 4 meter per second square. And the last law of motion is Newton's third law of motion, and it states that whenever two objects interact, the force exerted on one object is equal in magnitude and opposite in directions to the force exerted on the other object, and this law is also called action and reaction. In simple term, we will also here, in simple term, we can also say every action has equal and opposite reaction. So in general term, when we are writing mathematically, we can write it like this equation. Here the force on object A here force on object A, sorry, here force on object A caused by B is equals to force on object B caused by object A, and they are equal in magnitude, and we can see here there is a negative sign, meaning they are equal in magnitude and opposite in direction. Let's look at an example. A 60 kilogram astronaut is freely floating in a space and pushes on a freely floating 120 kilogram spacecraft with a force of 30 Newton for 1 second. So what is given here? Mass of astronauts, I will write it as ma, is equals to 60 kilogram. And what else is given? The mass of a spacecraft, I will write it as ms equals to 120 kilogram, and we are also given that a force of 30 Newton is felt by the spacecraft, and time is 4 seconds. We don't use any time so far, so we'll just keep note on it and don't worry about the time. And now let's move to section A. Compare the forces exerted on the astronaut and the spacecraft. So what are the forces exerted on astronauts and the spacecraft? So as we said, every force will have equal and opposite reaction, meaning the force exerted by astronaut on spacecraft should be equal to the force exerted on spacecraft by spacecraft on astronaut. So this is exerted on astronaut by spacecraft, exerted on spacecraft by astronaut, and these forces are equal but opposite in direction. So compare the forces. Basically the forces are the same but in opposite direction. And for the section B, let's see, the question is compare the acceleration of the astronaut to the acceleration of the spacecraft. Now we need to calculate the acceleration of the astronaut and acceleration of the spacecraft and see how different they are. So we said the force is the same on both. That means the magnitude of force is 30 Newton, right, in both cases. Because we are only interested in magnitude in this case, because we already know they will be in opposite direction, we do not need to worry about which is positive and which is negative, because they are opposite in direction to each other. So we will just calculate the magnitude. For now, let's look at the magnitude. So the force is equals to mass time acceleration, and we need to calculate acceleration for astronaut. In case of astronaut, force is equals to mass of astronaut, acceleration of astronaut, and we can isolate this acceleration. Then acceleration is given by force over mass, and force is 30 Newton and mass is 60 kilogram, which gives us 0.5 meter per second square. Similarly, force felt by spacecraft is equals to mass of spacecraft, acceleration of spacecraft. If we isolate acceleration, this will be force over mass, which is force is same, both astronaut and the spacecraft felt the same force, and this 30 Newton, and the mass is 120 kilogram. So the acceleration is 0.25 meter per second square. This will be 0.25. 30 over 120 is 0.25 meter per second square. So the acceleration is, we can say, in terms of direction they are opposite, and magnitude are equals to 0.5 meter per second square, and acceleration is spacecraft is 0.25 meter per second square. So basically acceleration are different, the forces are same, and the direction are opposite to each other.